you observe closely, electricity is being converted to light, sound, mechanical or kinetic energy. But this step is not direct. What we are doing is we are converting electricity to magnetic field, and then this magnetic field is getting converted into light, sound or mechanical energy. Okay, now how that works, I'll help you understand. And in this category 1 scenario, bulb and lighting, you can put it either in category 1 or 2. You will understand why I say that. In category 1, actually you are storing electricity in the mobile, right? And this storing in the mobile is actually in the battery, where there is a chemical energy. It is stored as chemical energy. And when you discharge, this chemical energy gets converted into electrical energy, right? So whenever you use electricity, electricity causes three things. Either it causes a change in chemistry, it causes a change in chemical form, like what is happening inside a battery. So this category 1 is classified as chemical effects of current. Chemical effects of current. Category 2, this is called as magnetic effects of current. So all the appliances that we use at home, most of them make use of magnetic effects of current. And the third one is called as heating effects of current. Okay, so what is happening? You know that current or electricity is a form of energy. Now that form of energy can get converted into three other forms. One is chemical energy, second one is magnetic energy, third one is heat or heat energy. Now based on how we apply or where we apply, these three forms of energy can be used. And depending on the application that we want, we can convert that. And sometimes you might be confused with the combination. For example, if you take a microwave oven, you might be thinking that a microwave oven is actually heating an object. Am I right? What do you do when you're cooking something or when you're heating water or boiling milk in a microwave oven? You will be thinking that the temperature is increasing. But how is the temperature increasing? The temperature is increasing by this electric energy, which is drawn from the mains, from the supply, is continuously used to create a magnetic field, which is also called as an oscillating magnetic field, which can create heat. So the application, that's the reason the microwave oven is still shown as a magnetic effect of current. Similarly, when you hear sound from a speaker, what is happening there? The electricity is used to convert that electrical energy into a magnetic field or magnetic energy inside a speaker. And that magnetic energy gets transferred into sound waves using a diaphragm. So how does a microphone work or how does a speaker work? They all have magnets there. So this electrical energy is making use of the magnetic effects of current to produce the necessary sound that we want. Okay, so the largest applications of electricity are usually in the second category, the magnetic effects of current. So today in today's session on electricity, we will be spending a lot of time on the magnetic and heating effects of electric current. The chemical effects you don't require much at this level, but I'll briefly touch upon that. So when we first start, I had defined that current is a form of energy. Okay. Now you might be confused that on one hand we would be saying that current is nothing but a flow of charges and so on. How does flow of charges become form of energy? Can you define that? How is flow of charges becoming a form of energy? Yes, anyone? How does the flow of charges become?
Electron need energy for moving.
Yeah. So electrons need energy to start to move from one place to the other, and the electrons are actually moving around pretty randomly inside any wire. Okay, they are always continuously moving. So when you are giving current, you are actually making these electrons move in a particular direction. So you are setting the direction. Okay, so current is nothing but the energy kinetic energy of charged particles. Okay, kinetic energy of charged particles. Now remember that these charged particles are mostly electrons. Whenever you have wires or whenever you have solid conductors, the charged particle that can move is always the electron. So in such case, you can say that it is the kinetic energy of electrons. Okay. These charged particles can be an ion in electrolytes. Or like for example, if you take a cell or if you take a battery, the charged particles are both electrons and ions. Okay, so what do I mean by this? I'll give one simple example. Now let's take a small cell like this, and let's say that this has some solution, and there are two electrodes. One is a copper electrode, one is a zinc electrode. Okay, now you take this wire and connect it to a bulb. Will this bulb glow?
No, sir.
Why wouldn't it glow?
There is no source of energy.
Yeah, so in reality the bulb will glow. Okay, there is a source of energy. It is actually called as the difference or the potential difference between these two. So if you have an electrolyte here, let's say you have CuSO4 solution here, and then you dip two electrodes. Remember that if you have both electrodes of the same metal, it won't work. You should have two electrodes of two different metals. So if you have two different electrodes, and in this case I have indicated that it is copper and zinc. The moment you dip this, what will happen? You have studied what is called as a displacement reaction.
Yes, sir.
Yeah, so what is a displacement reaction?
High reactive metal displaces less reactive metal.
Yeah, so you would have done this experiment in school where you take copper sulfate solution, which is blue in color, and you would have put a nail or something, either of iron or zinc. If you insert it, you will see that copper starts getting deposited on this. So what is the reaction that is happening? Zinc is replacing copper sulfate and it is producing, it produces zinc sulfate and copper. So what is happening is this copper is getting deposited on this electrode and it produces that brown color. Am I right?
Yes, sir.
So let's imagine what is happening here in this. So though you write this equation in a very, very simple manner, in reality, this doesn't happen in one straight step like this. So the moment you put this in a solution, what is happening is there is Zn, there is Cu2 plus. Copper sulfate does not exist as a molecule. It breaks off into two ions. Cu2 plus gets separated. SO4 2 minus gets separated. Okay. Now look, this sulfate ion, let's say what is happening on this case, there is zinc sulfate ion, and then there is copper. So what is the ion which is constant on both sides?
Positive.
Can you see that the sulfate ion is there on both sides?
Yes, sir.
It is not changing, no?
Yes, sir.
So what is happening to zinc? Zinc is becoming Zn2 plus, correct?
Yes, sir.
And copper, which was an ion, Cu2 plus, is becoming copper. Now, if zinc is giving out two electrons, then it becomes Zn2 plus. Am I right? Isn't it?
Yes.
And copper, if
Repeat
it is taking two electrons, it will become Cu, correct?
Sir, please repeat it.
Yeah. So if you observe the zinc ion, on the left hand side, zinc is an atom. It has no charge here.
Yes, sir.
So this zinc atom, if it were to become a zinc ion, if it has to get two positive charges, doesn't it mean that it has to give away two electrons?
Yes.
Yes, sir.
Correct. Similarly, if copper, which was already an ion, it has two positive charges. If it was to become neutral, then it has to take two electrons.
Yes, sir.
So what does this mean? That the zinc is giving away two electrons, copper is taking two electrons. Am I right?
Yes, sir.
Yes, sir.
Now come to this scenario, come to this figure. Now here, the moment you dip these two sticks, what will happen? Zinc will give away two electrons, copper will take two electrons. So from zinc, from the right side, from here, two electrons have to go to copper. How will they go? Will they go through the solution? Will they go through the solution here?
Yes, sir.
Remember that the solution has sulfate ions, SO4 2 minus. So there is already a concentration of negative ions there, right? So the electrons can't go through this. What will happen is the electrons will go through this wire. Two electrons will go like this. They'll go through the light. Then the light will start glowing. Then they'll go like this. Then the two electrons will come to copper. And here, the moment they come to copper, you saw that was copper ion was to absorb two electrons and then it had to settle. So you will see that copper is settling down. Okay. So whenever you have a battery, in the battery, what is happening is one side of the battery is willing to produce electrons like zinc here. Zinc is ready to give away two electrons. And another side of the battery is willing to accept two electrons. Like in the case of copper. Copper is ready to accept two electrons. what we will do is we cleverly design the circuit in such a way that these two electrons will move from zinc to copper, but they have to go through the circuit, and while going through the circuit they have to do whatever work we give it. Like in this case we put a bulb, so it has to glow. Or let's say we have put a fan there, the fan has to turn. Or in case you are putting a heating iron there, it has to produce some heat. So any circuit, any electrical circuit, basically it is charged particles going around. They have a lot of kinetic energy. We are harnessing that kinetic energy. We are making use of that kinetic energy to do a work that we want. In most cases, the charged particles are electrons. In most cases, in batteries and electrolytes, we do have ions also, which can move. Okay. Any questions here? Any questions here?
No, sir.
Okay. Now, how do we measure this current? How do we measure this current?
By glowing bulb.
So what we do is, we know that these charges are going through this wire. So we catch hold of this wire and we put what is called as an ammeter here. The meter which is used to measure current is called as an ammeter. The meter which is used to measure voltage is called as a voltmeter. There is another meter which is called as a galvanometer. It is not used to measure current, but it is used to detect. Even if there is a small current, this galvanometer can actually detect. Okay, so the design of a galvanometer and ammeter are very similar. Galvanometer is extremely sensitive. It can detect a current, but it can't help us measure current. An ammeter can help us measure current. Okay, now how does it measure? An ammeter, when we are measuring current we usually use the symbol I, is measured as amount of charge that is flowing through the meter in a unit amount of time, or the time taken to measure. Okay, now what is the unit of current?
Column.
Unit of current is actually ampere. Unit of charge is coulomb. What is the unit of time?
Second.
It is second. Yeah. So the unit of current, 1 ampere, is equal to 1 coulomb per second. So usually, if you look at your phone chargers, they produce 1 ampere current. So what does this 1 ampere current mean? It means that there is 1 coulomb of charge crossing that wire in 1 second. But how much is this 1 coulomb of charge mean? How many electrons have to cross if it has to be 1 coulomb? Any idea?
1 electron.
So here we will have to know the charge of an electron. Okay. So one electron has a charge of 1.602 into 10 power minus 19 coulomb. So I will approximately take this as 1.6 into 10 power minus 19 coulomb. It's a very, very small charge. The charge of an electron is extremely small, 10 power minus 19. Okay. Now, if this is the amount of charge of one electron, if it has to be 1 coulomb, can I write this as 1 coulomb is equal to some x number of electrons into the charge of each electron. Charge of each electron is 1.6 into 10 power minus 19. This is coulombs, and divided by, it has to be 1 second. So what will x be equal to? X is equal to, this will go to the denominator now, 1 by 1.6 into 10 power minus 19, or someone has given the right answer in the chat box that it will be around 6.7 into 10 power 18 electrons. So this is a huge number. 6.7 into 10 power 18, that is 6.7, and then you can write 67 followed by 17 zeros. Those many electrons cross that small wire which you use in your mobile charger. So those many electrons have to cross this wire to generate 1 ampere of current in 1 second. If the current was 2 amperes, how many electrons would go in 1 second? Yes. If the current was 1 ampere, we know that there are 6.7 into 10 power 18 electrons. If the current was 2 amperes, yeah, so it will be 2 times this. Yes, Tanvi has given the right answer in the chat box. It will be 2 times this. So it will be about 13 into 10 power 18 electrons. Okay. Now, if I give the question the other way around, you have 1 ampere current. In half a second, how many electrons will flow? In half a second, how many electrons will flow? Yes, anyone? In half a second, how many electrons will flow? About half of this. 6.7 divided by 2, which will be about 3.3. So Srishti and Tanvi have given the right answers here. Suppose I make this question a bit more complicated. I'll say there is a 5 ampere current flowing. Now I'll ask you how many electrons will flow in 1.5 a second if there is 5 amperes of current flowing. So the question is, there is 5 amperes of current flowing. How many electrons will flow in 1.5 seconds?
1.5 into 5 ampere current.
Yeah, so 1.5 into 5 ampere. So 1.5 into 5 into this 6.7 into 10 power 18. Okay, so you should be able to keep tweaking this number and keep be able to calculate. So the current I is equal to Q by T, charge divided by time, total amount of charge that is flowing divided by time taken, or this total amount of charge can be written as N into E divided by T. N into E is number of electrons into E. E is charge of an electron. Charge of an electron we know is 1.6 into 10 power minus 19. So suppose they ask you a question, how many electrons are required? Then you can rewrite this equation. Current into time divided by charge of an electron. Yeah, someone had a question, I guess.
Sir, what is mean by Ne? Sir, please repeat it.
Yeah. So Q is the amount of charge. Have you understood this part?
Yes, sir.
Okay. Now, where is this charge coming from? Charge is coming from electrons, all the negative charge.
Yes, sir.
So, if I know charge of one electron, if I multiply it with how many electrons are there, then will I get the total charge?
Yes, sir.
So, what I have done here is the same thing. This is the charge of one electron. This is the number of electrons that are there. You multiply these two, N and E. E is the charge of one electron, N is the charge, the number of electrons. You multiply those two, you will get the total charge.
Yes, sir.
So that is what is the written in the numerator. So sometimes they might ask you how many electrons flow. So what you have to calculate is N, or suppose sometimes they will ask you to calculate the amount of current. Then you just have to calculate I. Okay. So there are multiple ways to calculate uh, uh, current here. Sometimes there are also quite very interesting questions like, let's say there is an electron going around a circle like this. There is an electron going around a circle like this at a per certain speed. They'll ask you what is the amount of current flowing. How will you calculate that?
1.6 into 10 to the power minus 19 multiply into 1 electron.
N is 1. What about time t? In how much time is it completing? So there time t, what you should do is you should calculate in how much time this electron is completing one circle. That time you have to substitute here. Okay. Because we are interested in calculating, if you take any one point, let's say this point A is there, how many charges will cross that point A? That is what we are interested in. So this electron will cross this point A in the same amount of time that is required to complete one circle, isn't it?
No, sir.
Okay, let me put it this way. Now let's say you have a in your school you have a 400-meter track like this. Okay, in this 400-meter track, let's say you start the race at point A and there are 4 different points like this. Let's assume that you require 5 minutes to complete that circle, that entire one round of the track, along the track. Now if I ask you at the end of first minute, how many times have you completed one circle? How many times will you cross the point A? First minute you wouldn't have completed it, no, because you require 5 minutes. If you are starting from A, you would have just gone ahead slightly. Am I right?
Yes, sir.
Now, if I ask you after 2 minutes, will you complete one circle?
No, sir.
Will you at the end of 2 minutes, will you come till point A? You wouldn't be, right? You will still be somewhere in between. What is the case at the end of 5 minutes? After 5 minutes, would you have completed the circle?
Yes, sir.
So if I ask you at the end of 6 minutes, how many times have you crossed the point A?
So only 1 times.
If you count the starting also, if you are starting from A, then you have crossed it once. And then after completing one full circle, you are then crossing it the second time.
Yes, sir.
When will you cross it the third time?
So after 4 minutes.
After, yeah, 4 more minutes or 10 minutes, right? So one extra round is after 5 minutes, then 10 minutes, then 15 minutes, then 20 minutes, and so on. Am I right?
Yes,
Yes.
sir.
So even here, when an electron is going around a circle, you have to give in how much time will you complete that circle. Suppose in this case of going around a track, this case, you told me that you know that you need 5 minutes to complete, right? Suppose I ask you in, let me say, in 17 minutes, how many times will you touch the point A?
Sir, 3 times.
So
How
four
is it
times.
3 times?
The 4 times.
4 times. Why? How is it 4 times?
So 5 minutes required to complete one round.
Yeah.
So
So at the starting of the race, time 0, you are there at point A.
yes, sir.
5
5 to
minutes, you are there the second time.
yes, sir.
10
10
minutes, third time. 15th minute, fourth time.
time.
17th minute,
So in between,
you will be there somewhere in between. You will not cross there.
yes,
So it is 4 times. So similarly, here if you take this electron might be going around very, very fast. So you would be interested in counting how many times this electron is crossing this point A. So then what you will do is you will just put the in the denominator t where you have time taken, you will take that the amount of time this electron is taking to complete one circle.
yes,
Okay,
sir.
shall we move ahead? I'll have one or two questions for you based on this in the worksheet, so once you practice you will be able to understand this better. Okay, shall I proceed?
Yes,
Yes,
sir.
Okay, the next interesting topic of current electricity is where we have or where we are measuring when there is current flowing in the wire, it is not flowing very easily, there is opposition to it. Okay, the wire does not, though we call it as a good conductor of electricity, the wire does not let the electricity, the current flow very easily. So the wire has what is called as resistance. Resistance means opposition. It is stopping the charges to flow. Okay, so this resistance is usually represented by capital R. Okay, now how is this resistance measured? This resistance is seen as a ratio between R is equal to V by I. What is this V? V stands for voltage or potential difference. What about I? I stands for current. Now we have already defined I. We have told that I is nothing but the amount of charges that are flowing. What about voltage? How can you explain it in layman terms? Not a scientific definition. In a layman terms, what is voltage?
the current into resistance.
That is from this equation. If you rearrange, you will get V is equal to IR. That is very correct. But in a very simple language, if you were to explain what is voltage, how will you explain it to someone?
So speed of currents.
It is not speed of current. Speed of current is nothing but flow of charges. So it will come in the definition of current itself. See, voltage. You should remember two things about voltage. First one, voltage is the cause of flow of charges. Meaning, let's say if I put some water on the table here, okay. Now, will the water flow in a particular direction or not? Isn't it decided by if there is no incline or not? Would you agree?
Yes, sir.
So that incline is nothing but change or difference in height or change in height. So the moment you create an incline, what will happen? Water will flow from a higher point to a lower point, isn't it?
Yes.
If I increase this difference, will the water flow faster or slower?
So slower.
If I increase the difference, height difference,
The
let,
faster speed.
let me give you one example, one simple example. Let's say this is a flat surface and I have some water on this. There is a drop of water at the center. If I bend it like this to my right, what is happening to the water?
Sir, it will flow.
Water will flow.
It will flow towards the right. Now, if I make it much more steeper like this, will the drop flow faster or slower?
Sir, faster.
If I make it very, very close to flat surface, then
Sir, slower.
So
it will
slower.
slow down, right? So what does that mean? If the incline is more, it will flow faster.
Yes, sir.
Yes, sir.
So if the incline is more, can you compare this height difference between this point and this point? The height difference is higher. If this was flatter, this height difference would be lesser. Am I right?
Yes,
Yes.
sir.
So the more the height difference, the faster it would flow, right? So in the case of flow of charges also, in the case of current, voltage or potential difference, the word difference means it is almost like an analogous to this example. The greater the height difference, the faster it will flow. Similarly, in current, in circuits, the greater the voltage or the greater the potential difference, faster charges will flow or more charges will flow. Okay. If the surface was absolutely flat, will the water flow?
No, sir.
So similarly, in a circuit, if there is no voltage or if there is no potential difference, no current will flow. Okay. So the higher the potential difference, the higher the voltage, the faster or the more amount of charges would be flowing through that circuit. Is that okay?
Yes, sir.
So when you are measuring these two, there is a ratio which is called as resistance, which is nothing but a property of a material. What does this mean? This means just because you are applying the same potential difference, it will not produce the same current in different materials or in different wires. So if you have a copper wire, aluminum wire and a gold wire, if you apply the same potential difference along across these three wires, they will not have same current. The current will depend on the type of material it is. For example, gold has very, very good conductive properties, meaning gold has very low resistance. If the ratio has to be very low, if this ratio has to be very low, it means that denominator has to be greater. Am I right? Because voltage is same, no? Potential difference is same across the all three wires, so the denominator has to be greater. So in gold, where there is very low resistance, same potential difference will produce a higher amount of current. Okay. In, let's say, graphite, resistance is slightly higher. If you apply the same amount of potential difference, it will produce slightly lesser current. If you take rubber, rubber is an insulator. It almost does not allow current at all to pass through it. So their resistance is very, very high. It is not allowing charges to flow through it. So there, if you apply a voltage difference, current is negligible, very, very less. So did you understand this relationship?
Yes, sir.
So this is what is plotted in graphs also. So this equation is called as Ohm's law. So this Ohm's law is stated in a slightly different way. It is said that in a conductor, the current flowing is directly proportional to the voltage or the potential difference applied. Okay, which means V is equal to IR. This is also another way of writing Ohm's law. Okay, just the rearrangement of this. Now scientists became much more curious. Like I told you, gold has slightly less resistance. Now people started checking, does the shape of the wire affect the resistance? Any any thoughts on that? Do you think the shape of the wire will affect the resistance?
Yes, sir.
So people
No.
started exploring that. So they found out, in fact, resistance, though it is a property of material, it also depends on the shape of the wire. If your wire is very thin and long, it has a lot of resistance. If your wire is very thick and short, it has very low resistance. If your wire has a different type of cross section like this, your resistance is different. So people started studying how the types of or the shapes of these wires are affecting resistance. So they found out that resistance of a wire R is equal to or is dependent on length, and it is inversely proportional to cross sectional area. What is cross sectional area? If you cut this here, what do you see? You will see another circle here. If you cut this here, what will you see? You will see a box like this, a square. So scientists have discovered that resistance is proportional to length. As length increases, resistance is increasing. But it is inversely proportional to the cross-sectional area. If the wire becomes thicker, resistance is coming down. And they have multiplied it with a constant called resistivity. This symbol is called as rho. This is a Greek alphabet. It is rho. Okay. This is called as resistivity. Now, this resistivity of a material is always constant. Length can change, area can change, accordingly, resistance also keeps changing. Okay. Now, resistance itself has the units ohm, OHM, and we usually use the symbol omega, ohm, to represent ohms. Okay. It is named after the scientist who actually discovered the Ohm's law. Okay. Now, if this has ohms, current has units of ampere. What are the units of voltage, or what are the units of potential difference? Yes, what are the units of potential difference? Yeah,
Volt.
Uttara has mentioned that it is voltage. It is not voltage, it is volt. Volt is the unit. V-O-L-T. Okay. So the units of resistance are ohms. Units of voltage is volt. Units of current is ampere. Okay. And resistance can further be defined. We have also seen this component as well. Okay. Now, because of this resistance, you will see that heating happens. So when you see that something is getting hot, when in your geyser, for example, what is happening? There is just a wire, and when you pass current through it, you will see that it is getting hot. Or if you see the iron boxes, there is a very flat, very thin circuit of wires, and when you pass current through it, it is producing the heat energy there. Okay. Sudeepa has mentioned that volt is named after Alessandro Volta. That is correct. Okay. All the units here are actually defined or named after scientists who have done great contributions or who have made great contributions in the field of electricity. Okay. Now, the other thing is, we have also mentioned that electricity also produces lots of magnetic effects. So how do we define those magnetic effects? So for this, people have done some experiments. I'll not go into great detail, but you can just you would have seen this once, that let's say when you're at home, when you're at home, when your phone is ringing, you would have seen that the speaker of the television, or when the mic, if you are using a microphone, or if you are using a speaker or a headphone, you will see that its audio keeps changing. There is a humming sound which is produced, isn't it? Have you observed? Or let's say when you are in school, there is a guest who is carrying a phone, and let's say he has come very close to a mic and he is about to speak. If he gets a call, you will see that it produces a sound in the mic.
Yes, sir.
Yes,
Yeah. So that is because this phone, when it receives a signal, it is actually generating a magnetic field. So how is this magnetic field produced, or how is this magnetic field generated, is always given by what we call as the right hand thumb rule, which means, let's say this is a wire and the current is flowing in this direction. How is the magnetic field? The magnetic field will be in circles like this. Okay. But how do you know that? So you take your right hand, the thumb should point in the direction of the current. The thumb should point in the direction of the current. The way you curl your fingers, the way you curl your fingers will give you the direction of the magnetic field. Okay. So if in this diagram I have shown that this is the direction of the current, the fingers are curling towards me, or if you are repeating it, you will see that the fingers will curl towards you. That will give you the direction of the magnetic field. Okay. It is also interesting. Let's say the current is flowing in a circle like this. Current is flowing in a circle like this. Then you curl your fingers in that circle, the circular direction. The thumb will point to the direction of the magnetic field. Okay. So for both of them, you can use this. Finally, what is this telling us? It is telling us that whenever there is a current, there is a magnetic field. And what is the direction of that magnetic field? This is given by the right hand thumb rule. Okay. Now, the first person to do this experiment and actually find out that there is a magnetic field was Orsted. So he used the magnetic compass, he kept it at different places, and then he figured out that you change the current, the magnetic field will keep changing. If you reverse the direction of the current, the magnetic field will keep changing. So how is the direction of magnetic field to be predicted? He gave the right hand thumb rule. So you just use the right hand. If you take the thumb as the direction, if the current is flowing in a straight line, you use the thumb to show the direction of the current, then the fingers will tell you the direction of the magnetic field. If the current is flowing in a circular direction, then curl your fingers along the direction of the current, then this thumb will tell you the direction of magnetic field. Okay. Now suppose I ask you, if I were to produce a circular magnetic field, what should be the direction of current? Should it be in a straight line or should it be in a circular path?
Say straight line.
It should be in a straight line because your fingers will be along the magnetic field, thumb will be the straight line, right? So if you have to produce a parallel magnetic field or a magnetic field which has straight lines, the path of the current should be in, it should be in circles, right? It should be in a circular direction. So this is what we routinely apply. Like for example, if you go to a simple case of a CT scan or a MRI scan, have you ever wondered why they have these circular tubes into which you are sent? Any idea?
Sir,
So if you have those circular tubes, you are sending the current in circular direction. So what type of magnetic field will it produce?
say straight
It will
line.
produce a straight line magnetic field, or sometimes we refer to it as a parallel magnetic field or also a uniform magnetic field. Okay. So whenever they do an MRI scan, actually what they are doing is they are inducing a magnetic field and then observing what is happening to your brain or any body part. That's why MRI stands for magnetic resonance imaging. Imaging because they are taking a photograph. Okay. So when they apply a magnetic field, how is your body part responding? The photograph is taken. That's why it's called an MRI. Okay. So whenever you have this connection between a magnetic field and a current, you have to keep remember this right hand rule. Okay. Now it is named after several scientists. It is named after Maxwell and so on. So you need not get confused after whom it is named. Okay. The next important aspect, or maybe the last part of today's session, is there is a connection between electric field, electric field, magnetic field, and motion. Like if you take a fan, have you ever wondered why the fan is always going around in one direction? Why not in the opposite direction? Any guess?
Sir, because current is flow in one direction.
Yeah, it is partially correct because current is flowing in one direction. It is at the start. So when you are using a fan uses a capacitor or a starter inside it that starts the fan, and it always lets the current flow in one direction to help it start. And once it starts, it continues in that direction. Okay. Now, what happens in a fan is basically this current which you supply, it is creating a magnetic field. Now, you know that when you bring two magnets, like poles repel. So if you are trying to force these magnets to come very close to each other, what will happen? You will see that they'll slip like this. Then there will be some movement, right? There will be some movement in one particular direction. So that is what we make use of. So all the appliances which use current to create motion are actually falling under the category of motors. Motors. Whether it is the wet grinder in your kitchen, or whether it is the fan, or whether it is the water pump, they are all motors. They are using electrical energy to convert it into motion, or mechanical energy, kinetic energy, right? So what do they are governed by Fleming Fleming's left hand rule. Now, this Fleming's left hand rule helps us decide in which direction the object will move or the fan will rotate. Okay. Now, that is given by your left hand. Take your left hand, close the fist like this, and I'll keep explaining each component, and then you will have to open one finger after the other. Okay. The first finger you have to open is your thumb. Point it out this way, and I'll write F here. So F on the thumb. The next one is your forefinger. You have to open it in a direction such that it is perpendicular to the thumb. So the forefinger, this is representing the magnetic field. Magnetic field is usually we use the symbol B. Okay. Then you have to open the middle finger, but you have to open the middle finger such that it is perpendicular to both the thumb and the forefinger. So if you observe my hand here, the thumb was pointing in this direction, the forefinger was pointing upwards, but the middle finger is actually pointing towards you, right? And this middle finger, this is representing current, direction of current, FBI. This is a nice term to remember, FBI. So F is representing the thumb. The direction of F actually stands for force here. So in the direction that you apply force, you will see motion, right? So if you are seeing force here, then you will see force. This B represents the magnetic field, I represents the current. So you should be in a position to sort of turn your wrist around and apply. Just observe of these three, if you know any two, then you can predict the direction of the third. So if you tell that your fan is always moving in the clockwise or the anti-clockwise direction, what you have to do is put down that schematic diagram, then you apply this. The current will be flowing, the I part will be flowing in one direction. There is a magnet inside. It's actually not a permanent magnet, it's an electromagnet. So the moment you give it some current, it will start behaving like a magnet. Then that direction is given by B. And in which direction are these two applying a force? In which direction are they forcing the fan to move? Is given by the F or the thumb. Similar logic is also applicable for these very high speed trains, the super fast trains that you see. uh, across the globe, they are also electric trains, right? So they actually levitate. They are not running on wheels. They are actually, if the moment they are switched on, they actually slightly raise upwards and then move forward. So to move forward, there is a force which is applied in a direction, in the forward direction. So the moment you do that, you will get to know if the train has to move forward, the current has to flow from this direction, my right side to the left side. The magnetic field should be pointed in the upward direction. So this will tell you how the trains will move forward. Let's say you have to apply a reverse gear. If you want the train to move backwards, you have just turn your hand like this. If you observe, the magnetic field is still upwards, just the current direction is reversed. If you turn it this way, you will see that the train is moving forward. If you try and turn it this way, you will see that the train is moving backwards. So you might be wondering, how is it that an electric uh, bike now has a reverse gear? It is what they have done is, in an electric motor, you send the current in the opposite direction, it will start moving in the opposite direction immediately. So by using this Fleming's left hand rule, you can actually predict this directions, or in which direction the motor is going to move. Okay, so I'll stop here. In case you have any questions, you can ask. Otherwise, we can continue tomorrow. And
Sir,
day after, you will be having some worksheets where you will be solving some problems using these. Yes, Ria, you had a question.
the concept of MRI.
Yeah.
The
Okay. So we don't have sufficient time for discussing it at length, but I'll tell you what it is. Okay. Now, let's take a let's take your hand. Okay. Now, what is your hand made of? What is your
so
hand made of?
some muscles, blood, bone,
Muscles, blood, then
bone,
bone. Yeah. So let's take these three components: muscle, blood, and bone. Okay. What is the bone made of? What is the bone made of?
so don't know.
Bone is mostly calcium, isn't it?
Yes, sir.
Bones are mostly calcium. Is calcium magnetic?
Yes, sir.
If you touch, let's say, an iron object, does your hand attract it? Or if you hold a magnet, will your hand be able to attract that magnet?
No, sir.
No, right? So your hand, calcium, the bones are non-magnetic materials. Okay.
Yes,
However, if you take your muscles, are they magnetic? What?
no, sir.
Yeah. So let me ask this question. What are the muscles made of? Muscles are made of cells, several cells, and these all cells have mostly water content, right?
Yes, sir.
Our body is mostly water, no?
Yes, sir.
Yeah. So the beauty of a water molecule is it has what is called as a dipole moment, meaning every single water molecule can behave like a small magnet if you apply some current. But in our body, water is sort of pointed in all directions. That's why your body is not magnetic. Okay. So we use this property when we apply a magnetic field. If your body is behaving in a particular way, it can tell you how much water is there available there. So if there is more water concentrated at one place, that part of the body will behave differently as compared to a bone. A bone has no water in it. and it has no magnetic material in it, it will behave differently. Am I right? So if I take a photograph, the parts where there is a lot of water will look differently. The parts where there is no water will look differently. So depending on how different parts of your body, again based on the concentration of water, based on how much water is there, you will see that differently. So what happens is, let's say that you have a fracture in your hand. It means that there is a crack which is generated, and then there is some fluid that will go and get stored there. If there is fluid, it means that there is water, which means that water gets highlighted when you take a photograph.
Yes, sir.
So what I am explaining is a highly simplified version. In reality, is much more complicated, but it is just that the way each component behaves when you apply a magnetic field is what is taken as a photograph. Okay, so in an X-ray, you take one photograph, and it is like you try to capture all the details. But if you are in an MRI, what we do is you take the same photograph of the hand. You will take one photograph here, then you will go 2 millimeters inside, then you will take another photograph here. It's almost like you are slicing your hand into several photographs. So each photograph will give us more and more details. So that's why even when you do a CT scan, they'll say 24 slice, meaning they're able to sort of break that into 24 different pieces and observe each piece differently. That gives you much more details. Okay, so if you're really interested in it, maybe I'll take a separate session outside this to explain how each of these MRI, PET scan, CT scan work. But for this session, I think this should be sufficient.
Okay, sir. Thank you, sir.
Thank you.
Thank you, Praveen sir. The session was definitely very, very interactive and very informative. I thank all the students for actively participating in this session, and we will be continuing with another topic tomorrow. So please, I request everyone to join in time so that we can utilize each and every second of this session. And in the chat box, you can see a link that has been shared. Please fill this form. Praveen sir, please give them 2 minutes to copy this link that I've shared, and we will see you. We will have 2 more sessions this week, and we will meet after Diwali. Until then, keep studying, and I don't want you to miss out on your festivals. But the exam, the NTSC exam, is quite near, so I would like you to take this a little more seriously. And thank you, students, for joining. And all right, see you tomorrow, guys. Please fill the form.
Meanwhile, I think Vaishnavi had raised her hand. She had a
Yes,
doubt.
please. Yeah.
Vaishnavi, can ask your doubt.